Welcome to Natural Habitat Adventures, Daily Dose of Nature. Today's topic, Secrets of the Deep, Hydrothermal Vents Beneath the Sea, presented by NatHab Expedition Leader Melissa Silva. I'm your host, Rob Mess. Thank you all so much for being here with us today. Over to you, Melissa.
Thank you, Rob. Thank you, everyone, for being. So let's start with this amazing presentation. I hope you all enjoy what I have for you today. So my name is Melissa Silva. I'm a marine biologist. I live currently in Mexico City, but I was living in Puerto Vallarta City some years ago. I studied there. Then I started my master's degree on the peninsula of Yucatan and the Gulf of Mexico. And during all these years, I've heard of this specific area of the ocean. And when I get to read more about that, to learn more, I was fascinated by these regions because it's I can consider that this as an alien world within our oceans. So I hope you enjoy this presentation, this webinar today, and find the fascination that I had. We can share that for after this webinar, after what I have to say. So we can start by thinking of how the life is as we know. If you think of living organisms on Earth, you might think on something that we have here on this slideshow. But basically, when we think about the life on the surface of our planet, we always have to go back to the very basic food source or the very basic energy source, which are the plants, the autotrophs. These organisms, they create their own nutrients. Their food source is water and the soil and the minerals that are in there. But in order to convert all of that into something nutritious for them, for growing, for reproduction, they need some energy to transform all of these inorganics into organics in their bodies. So they have the sun energy, the light energy to do so through the photosynthesis that we all have heard of. But what happens in the ocean? When we think about the ocean, well, on the surface, we do have some sunlight coming in, but on the bottom, we don't. So most of the ocean is bottom. Most of the ocean is deep waters. 5% of the water that is covering our surface on the planet, it's an area that we call the photic area, or the area where it has the sunlight. And the 95% of the rest is an aphotic area. So that means 95% of the ocean does not receive sunlight. On the photic area, we also call this the epipelagic area. If we have clear waters, it's most of the times up to 200 meters, 650 feet, where we have all of the sun, all of the wavelength coming into the water. So here is where we find phytoplankton, which is actually the most important oxygen producer in the world. And here is where we find, for example, the coral reefs, and all of these organisms or these life forms are based primarily on the photosynthesis of these phytoplanktonic organisms. If we keep going deep down on the ocean, there is this section that we call the mesopelagic zone, that in case that we have crystal clear waters, we might have sunlight, some wavelengths going all the way to a little bit more than 3,000 feet. And still here we find abundant and diverse life forms because of something named vertical migration. That means that mostly small fish or zooplankton is moving up and down with the sunset and the sunrises, following the phytoplankton that is moving at the same time up and down with the currents and with the changes of temperature or self-propelling, following the light and the food sources. So that's why, for example, we have a lot of the fisheries that we have nowadays occurring in this zone, a little bit in deeper waters rather than the photic zone. So it's a very abundant area. It's a abundant biomass on this area, and well, this is the beginning of the adventure in these deep dark waters. Then right under 1,000 meters or 3,000 feet, we have the bathypelagic area or the midnight zone. Here, we basically don't have any light, any glimpse of light. And here is where we find bioluminescent animals or organisms. But still, we have abundant life forms or diverse life forms. A lot of these have very strange or funny shapes, but all of those are adapted to extreme pressure underwater and the lack of specific or stable food source. So whenever they find something to eat, they need to catch it. For example, the goblin shark, they need to catch fish or mostly they feed on fish. But let's say a squid or an octopus, and they need to grab it and don't let it go. So that's why they have this adaptation of the big jaws going out of the skull and getting the food. The same as the gold eel. This one, I'm pretty sure the pelican fish, I'm sure you have seen that one with a big mouth space. So they can get a lot of food and they can get catch and don't let go the food. But still, they have some source food, food source that is not big fish or big animals. This is called marine snow, and basically it's all the debris from the surface. Is poop pellets, basically, from the animals above. A little bit of inorganic matter that they might find useful for the nutrition. And basically, that's the main source of nutrition that they can find on the bathypelagic area. So all these pellets or these the grains of organic matter are sinking, dropping down, and these animals and this in this environment, they are catching what they are getting right there. Right below the bathypelagic, we have the abyssopelagic zone, and this is actually kind of like the average depth of the ocean, 4,000 meters, 4 kilometers, or 13,000 feet. And here still we find some living beings, mostly, of course, animals, because once again, we don't have sunlight in this area. So there's very common to find jellyfish here, to find sea cucumbers, like here, some starfish, some echinoderms, furas, and starfish as well. And one characteristic fish from this area is the tripod fish. It's a very common one on the abyssopelagic zone. And it was thought that this area was just a large plain, empty area on the bottom of the ocean. It was thought hundreds of years ago that the ocean was all level, that once you reach a certain depth, it was level all around the world. But well, eventually with the new technologies and more researchers, they found out that there's basically another geological world under the water. So we have plains, but the plains are broken by either trenches or mountain ridges or hills. So it's a very dynamic area under the surface. But still here, the food is very scarce, and the main food source that the animals living in this area is what we call falls, whale falls, tree falls, and basically any big animal that cannot be fully consumed on the surface of the ocean will sink down and will give nutrients to the animals that live down there. And basically, these areas, the whale fall or the shark fall, for example, they will become an ecosystem for a matter of months or even years. So they will provide food for these organisms for many time. And at the end, not even bones will be left out, for example, from the whale falls, because there are very specific organisms, in this case worms, that actually feed on the bones of these carcasses. And then we arrive to the adult pelagic area. These basically only these are the trenches. These are the deepest areas on the ocean, and these are associated to subduction zones on the tectonic plate boundaries. So the deepest point here is the Marianas Trench. These are some of the trenches that have been discovered in the world, and you can see they are associated, for example, here on the West Pacific. They are associated to the Ring of Fire, to this very active tectonic area. And the Mariana Trench is almost 11,000 meters, 11 kilometers. And so actually, if you put the Mount Everest from the very sea level of the mount on the bottom of the Mariana Trench, you still have 3 kilometers up to get to the surface. So just imagine the deep of that. Still, there is life in those very deep areas. This is an amphipod. This is it's a crustacean, very similar to the shrimps. You can see it's about like 2 inches big, more or less, 1.5 inches big, and it is found in these areas eating the leftovers from the above world. And still, in this specific area of the Mariana Trench, they found a fish living nearby some hydrothermal vents. And well, so we know there can be fish, there can be other species living in these very deep areas. So, well, as I mentioned, in these aphotic zones, we don't have photosynthesis, food is scarce, but still they have certain sources, like the marine snow I mentioned, the whale falls I mentioned, and the hydrothermal vents. This is one of the food sources for the organisms living in the deep sea. So the hydrothermal vents have a geological origin. In average, they are the 7,000 feet deep, more or less. We can find some on 800 meters that are 2,000 feet, more or less 2,000 feet. And then from there, all the way down to the deepest point of the ocean, we can find hydrothermal vents. And personally, I consider them submarine oases. I hope you can share that with me as you know a little bit more about them. But so let me show you what we have learned so far. So it's less than 40 years, 1977, when they discovered the first hydrothermal vent in the Galapagos Rift. And they had, since 5 years before, they had certain clues, some geologists and geophysicists, that there was something going on under the water. They thought they were underwater volcanoes. And then they found out that there was something different, and they actually were not expecting to find life at this depth and away from the solar energy. So I have an audio that I will play right now from Jack Corliss, one of the men that was in the Alvin submersible when they saw the hydrothermal vents. They had some clues, they had some photos from previous missions, non-tripulated, but this is the moment when they saw it for the first. So I think you can hear the excitement on his voice when he realized that there was hot water coming from the bottom, but there was associated to, he mentions dandelion fields and crabs. I will show you some of those organisms. So well, after that, there were many more investigations on the ridges for looking for the hydrothermal vents. And this is an actual map, accurate from the date, of where we find hydrothermal vents. So basically they are all around the world, as you can see. And as I mentioned, they are mostly associated to the divergent boundaries, the mid-ocean ridges, where the ocean is separating, its new crust is forming, but still we can find them in the trenches. So why they are more associated to the these mid-ocean ridges? Because we have cracks on the surface of the crust, on the surface of the ocean bottom, and the crust is very thin, so it allows the water to mix with the minerals that are here, and there are areas where the water filters down and then happens something like this on this diagram. So basically this is not on a scale or anything, so just very illustrative way on how hydrothermal vent works. So the seawater that is very cold on these depths comes in the cracks of this spreading area, and then it goes in to the, or very close to the magma, to the melting rocks on this named reaction zone. So there are a lot of chemical reactions, there are a lot of physical changes in the water and also in the rocks there. So they mix, and the water gets a lot of elements, a lot of minerals from the rocks around, and the water goes up, down. You can hear the audio recording. Okay, 1 second. Oh, shoo. Okay, let me see. I will try to put that in a moment. But so what I was saying is that the water goes in here, comes through the opening on the crust, and then goes out to the water column, and it distributes around this area, where in some areas the sediments, the minerals, are placed on the ocean bed, and this is linked to something that I will mention in a moment, the seabed mining. Okay, so let me see, how can I play this? Well, we will do that in a moment, Rob. At the end of the webinar, I will try to do that again. So well, the hydrothermal vents can have different coloration depending on what minerals they have is diluted in the water. So we have white smokers that have mostly barium, calcium, silicon. We have the black smokers that this basically has iron sulfide dissolved on this. But we also have clear hydrothermal vents. We have these that are called diffuse flows, or the shimmering water that they found on the Galapagos reef. So as I mentioned, they didn't expect to find any life form, any living form in the area, due to the extreme conditions of temperature, no sunlight, the pressure that is down there 1,000 times more than on the surface of the ocean. So it was until 2 years after the discovery, 1979, when the biologists had the opportunity to go down there and study the communities that are surrounding these hydrothermal vents. So I will show you some of these, but first, how do they survive without the sunlight? So we, well, the scientists found out that basically all of the organisms living here rely on chemoautotrophs that are either archaeas or bacteria, microbes that transform the minerals, transform all the inorganic matter into sugars, into carbohydrates. So they can be free living, as I mentioned, creating these mats, this purple coloration. Those are bacteria filaments. These white mats as well. They can be any color depending on what mineral they are working with. So what happens here is that all the organisms, all the other animals that live around the hydrothermal vents, they kept or they capture the bacteria within their bodies or in their gills specifically. They can have either specific areas like this trophosome on the tube worms where the bacteria is, and they are getting the chemics from the environment. In this case, for example, hydrogen sulfide or methane, it can be too, and then they can combine that and use the water and the carbon dioxide that is in the water as well to transform that into sugar. That is what they need to survive, sugars, and well, they release some other sulfur compounds that are on the ambience later. So we call this chemosynthesis, and opposite to the photosynthesis, here on the chemosynthetic area, we find that these organisms use the sulfides as the source of energy instead of the sunlight. So that's basically one of the main differences between one and the other, and that's why they have the ability to survive in these environments. So let me show you some of the organisms that live here. This is a mussel that are a group of mussels. It's a genera that are living here on the hydrothermal vents, and well, they can reach very large sizes, very big sizes. So they have, let's say, cousins that live on the surface, and they are 3 times bigger, living here by the hydrothermal vents. Also, we have the giant clam. You can see why they call it giant clam, almost 1 foot long. And as you can see on this image, with all the clams scattered on the basaltic seabed floor, we call these, the scientists call these clumps, clam bakes, like a bake area for the clams. And something that is very notorious and very important, and something that still keeps bringing more questions rather than answers, is that these specific organisms, these mollusks, they are on the substrate that is more or less, let's say, 10 to 15 degrees Celsius degrees, and then the other half of the body, the part that is on the top, they are almost on freezing temperatures, 2 to 4 Celsius degrees. So they have this like thermic shock, so marked in one and the other half of their body, but they can survive to that. They can cope with this and survive and thrive on this. So the most characteristic organism, the giant tube worm, this animal can reach a length of 9 feet, like 3 meters more or less, and basically all of it is just the area where the bacteria is living. All of the body basically is a sac with bacteria that are transforming the minerals from the water into sugars, into nutrients. And this red plume right here, that's basically just the area where the worm exchanges the chemics and breathes in and expels some other compounds that are not needed for that. So The exoskeleton of the tube worm is made of chitin, just like the shrimp exoskeleton or the crab's exoskeleton. So it's a very resistant, but at the very same time, kind of like flexible, so they can move and follow the flow of water while they are growing. Oh, this is something very amazing. The Pompey worm. This is, so far, this is the animal that can tolerate the hottest environment on Earth. They can tolerate up to 176 Fahrenheit degrees on the body area, right here, that is attached to the hydrothermal vent. So it's an amazing adaptation that they have. All of these bristles that you see on the body are covered with bacteria that are both protective to the body of the worm, and they are giving the nutrients from the chemosynthesis that they are doing. This tentacle-like area is the head, and those are the gills. So basically, the body is in the hot water, in the water vent, and the head goes out looking for cooler water to breathe, to get the oxygen for the bacteria and for itself to survive. So it's a very amazing adaptation that they have, and they are still under research on how they survive on that. This snail is a marvel thing. They found this in 2003, and there are only 3 vents that are located on the Indian Ocean that have this kind of snail, this species of snail. So basically, they are endemic to these 3 vents. And these ones, for example, on the other side, instead of having the body covered with the bacteria or the bacteria within the whole body, they have a specialized organ nearby the gills, where basically a bag where they keep the chemosynthetic bacteria, and they give the oxygen there, and the bacteria gives back the nutrients. So sorry, the oxygen and the sulfides and all the other chemics that the bacteria needs. In this photo that you see down here, you see 2 different species of snails, but still the scaly-foot gastrop, they can come in different colors depending, once again, on the minerals that the hydrothermal vent is expelling. So the yeti crab, I'm pretty sure that you have heard of that before. It's a very famous and very charismatic, I consider, organism from the hydrothermal vents. They are found basically in all around the world, and the characteristic is this hairy, those are not hairs, but we call them hairy arms, in which on which they actually farm bacteria. This is one of the claws, and right here on the bristles, on the hairs, they have the bacteria, and they just put their arms on the hot fluid from the vent, coming from the vent, and then the bacteria do their thing, and eventually they will harvest the bacteria from the legs, from the hairy legs. There are only 5 species that have been described, although they have been found all around the world. There are only 5 species described of this type of crab. Then we also have shrimps, albinocarididae shrimps, and the very cool thing about these organisms is that they are very tiny, but they can be found in very large numbers, like this one on the photo, or they can be found more like scarce dispersion, and they can adapt depending on how many shrimps are in the area. So when there are big numbers, like on this photo here, they will become more reliant on the bacteria that they have in their bodies, on the chemosynthetic bacteria, and they will eat the bacteria from the mats that are from the outside of the vents. But when there are less shrimps living, there's a less not diversity, biomass on shrimps, they can become carnivorous. So they have the ability to change trophic levels, we say. So instead of becoming first consumers when they are many numbers, they can become second consumers or carnivorous when there are less numbers of shrimps. So it's an adaptation that they found out that it's, I consider that to be very surprising. There are also top predators in the hydrothermal vents. The octopus, vent octopus is one of those. This is endemic or located only on the hydrothermal vents. That's why they have this name, Vulcanoctopus hydrothermalis. And well, they can tolerate a gradient of temperatures going from almost freezing conditions to almost boiling water conditions. So they can move from closer to the vents to a little bit away from the vents, looking for food. Basically, they feed mostly on some crustacean like the name amphipods, that they look very much like short-tailed shrimps. They're very tiny, and they are also feeding on crabs. Those are like the two organisms that they are proven to be feeding off. And they are thought to be blind because they don't have iris. They didn't found an iris on the eyes, and a specific nerve organ in the brain associated to vision. So they very much touch everything instead of seeing. Okay, so well, now we know some of the species. We know there is a very different temperature in the vent area and the chimney area and the areas around. So we call this ozonation. There's a gradient ozonation in this area. The water that is coming out from the chimneys, the hydrothermal fluid, is super hot. It doesn't have, it's anoxic, it doesn't have any oxygen on it. It has minerals, it has toxic compounds on it. It's very acidic, but then it mixes with the seawater, deep seawater, that is almost on the freezing point. It has a little bit of oxygen. It has a more neutral pH. So when we have this kind of interactions, we have a specific zonation depending on how resistant an organism is to the physical and chemical changes on the environment. So in this diagram that I have here, we have on the left the area with the highest temperature, but also the highest productivity due to the bacteria associated to the temperature on the vents. And then we have, for example, the Pompeii worm. That is the one that lives the closest to the vents. And then as we go on the image to the right, as we go away from the central area of the hydrothermal vents, we call the periphery of the vents, we see less and less diversity, and some organisms that are there, let's say, opportunistically. For example, some crabs that come on this area, but that only comes here when they find something to eat. They tolerate a little bit of the conditions here, but then they move out and then they come back. So basically, we call that ozonation. And well, there was always something associated to these areas. As I was doing my research for this webinar, did life begin at deep sea vents? Well, there are many clues that tell us it's very likely. The ideal conditions for that are given. Some organisms like the archaea microbes are found there, and those are one of the most primitive organisms on Earth. The compound that is coming on this fluid from the chimneys has some complex organic molecules forming around. So those are the blocks of life that are in the very basic form. And another point on favor, another thing that tell us like it's very likely that the hydrothermal vents were the very origin of life on Earth, is that it's a protected area from the radiation from meteorites on the early stages of Earth. So actually NASA is working over there looking for like clues or keys to look for life outside of the Earth in other areas of the universe. Well, still, even though it is so deep down, the hydrothermal vents face some threats. One of those is the deep sea mining. As I mentioned, if you remember, when the plume of fluid is going away on the water column, and the minerals and all the compounds are sedimenting on the sides of the hydrothermal vents, well, we have some nodules of zinc, cobalt, iron, and other minerals that I don't remember, but that are very, very important nowadays with the electronic industries, for our phones, for our television, the computers. So there are a lot of talks about mining the deep sea. Unfortunately, of course, there will be some side effects. And what the community, the researchers and the protection community for these areas, what they are trying to do is to put as many species as they can, as fast as possible, into the red list, so that they have certain protections and the environment over there is protected as well. If you want to know more about that, because it's a whole different and complete topic, I recommend you to go into this website. They have a lot of information in both the deep sea mining and well, the hydrothermal vents and the deep sea communities associated. So basically that's it. Thank you very much, and let's see if I can show you that amazing sound, the voice of the geology. So Rob, that would be it. Let me know if there's any question.
All right. Thank you so much. Now, before we start in with the questions, I would like to remind everyone that you can submit your questions via the question field in your control panel. So do we know what the temperatures are at these hydrothermal vents?
That's it. Yes, the maximum is about 300 Celsius degrees, which are 700 Fahrenheit, I think. Let me go back to this one moment. Right here, 350 Celsius, 600 Fahrenheit, 660 Fahrenheit, more or less. So that's like on the very center or very fluid coming out of the crack on the ocean floor. So that would be like the hottest area of it all.
Got it. Thank you. So do these hydrothermal vents ever close?
Yes. Yeah, actually, researchers estimate about like 20 to 50 years for the hydrothermal, when it's forming, blah blah blah, and then it gets to like the climax of the formation, and from there, like 50 years ahead, they will turn off, let's say, because basically that's what happens. They are moving with the crust, so they are going away from the this reaction zone. So they are moving away and they cool off and they basically turn off or die, both the hydrothermal vent and the and the ecosystem around.
Can any of the animals or bacteria living near these vents that close, can they migrate to other ones?
Yes, actually, what happens here is that when they are mating, when they reproduce, they expel most of these organisms, the clams, the worms, the crabs. They expel the eggs and the sperm to the water column. They release all of the gametes to the water column, and they move away with the currents. But of course, they will go somewhere in that ocean, mid-ocean reach, and they will find eventually, excuse me, they will find a hydrothermal vent that is either already formed or that is just starting or young.
Are humans ever the cause of these vents being destroyed, such as mining?
I think since this is something like very recent, I think that we don't have like really like a hydrothermal vent destroyed by the mining per se, but it is associated the mining and the, remember, we don't only find them like very deep in the ocean, we can find them from on the what was that 2,000 feet and beyond and below, and on 2,000 feet and a little bit above, we have the trolling nets that are catching, for example, shrimps or octopus or the flounders. So all of these bentonic areas are being basically wiped out by this kind of fishery. So in any case that there is a hydrothermal vent or a diffuse flow, that hot water coming out of the seabed, they of course will be destroyed. So well, that's so far that's the like the only one that we know that is directly impacting the hydrothermal vents. But well, if the deep sea mining is approved, we will have a little bit more of a problem there.
So are some of these creatures ever used for human consumption? Do we ever go near the thermal vents to fish or to get crabs or shrimp?
Yeah, well, they mention about like, well, this can be a source of food for humans, blah, blah. But then there were some other studies where they noticed that these chemosynthetic bacteria that the animals have, like the clams, for example, that is the one that I think of, the bacteria also has some toxic compound that is expelling, and the clam is, and the mussels, those are keeping those toxic compounds as a way of protecting themselves from predators. So in any case, if we are able to eat one of those, I'm pretty sure that they can be toxic to humans because of this it's called bioaccumulation of minerals or toxins or compounds that are left after the chemosynthesis. So I have never heard, I didn't read any information about human consumption in all these years since their discovery. And what I read was that they have some toxins in their body. So I don't think we should eat those, honestly.
I agree. That's good to know. Thank you for that.
Yes.
How big is the Yeti crab? They look like they're very small.
The Yeti crab,
Yes.
they are about 12 centimeters long, which is 4 inches, I think. What? No. Yeah,
So,
like 4 inches, I think. 12 centimeters.
gotcha. They're tiny.
Yeah, so here you can see this is the 2 centimeter thing. So dos, cuatro, ocho, 10, 12, 14. This is like 16 centimeter long, and that's kind of like the average of the Yeti crabs, the 5 species. So it's like this, more or less.
Great. Thank you for that. So, do we find any species that have been mixed to make new species, or are there any species that haven't even been classified yet that are found?
Yeah, there are some species. I found some information about species that are just very recently discovered in 2013, 2018. And most of those are either microbes, bacteria, archaea, crustaceans, like the amphipods I mentioned, the small little shrimp-like crustaceans. And what else was discovered very recently? Basically more like small to microscopic organisms, because of course the big ones that you can see on naked eye, you can identify it a little bit before than the others. So yeah, that would be the ones that I've heard of. For example, there was this study of it was on the Atlantic mid-ocean ridge, and they were sampling all over the area, like 12 different vents, and they found between 300 and 500 different microbes, different bacteria and archaea that they hadn't identified yet. So they had to do PCR and the genome sequences and that. So they can identify all of those, and they found out there were like hundreds of new bacteria in the hydrothermal vents associated to these communities that have not been discovered. So those would be the ones that are recently found.
That's pretty amazing. After all this time, we can still find new life on Earth.
I know. It's amazing.
All right, well, unfortunately, that's going to be the last question that we do have for today, Melissa. So I'd like to throw it back to you for your closing comments.
Okay, so I would like to try to record this because I think it's very, if not important, I think it is, it gives a lot for the experience. The voice recording of the doctor Corliss. So if you allowed me, let me just do something, and I will go to the.
Unfortunately, we're still not hearing the sound. I'm not sure why, Melissa, but that sound is not coming through to us.
Okay, I think I recorded it. Let me play it back for you. Can you hear it now?
We cannot.
Oh, so I don't know if you were able to hear something now or not. I will try my best.
It was difficult to hear, unfortunately.
I
But thanks
know,
for sharing.
so bad, so bad. But they were very excited to find the crabs and the water coming out from the ocean bed. So that I wanted to share that with you. But well, you can always go on internet and Google the discovery in the Alvin submarine. So my final comment will be that I really like this quote from Jurassic Park movie that life finds a way. So with this webinar, I think we can prove that life found a way to survive in a very different condition, in a very strange way, but that give us hope that we can we will survive. We will find a way to go beyond of what we have now. So basically, that would be the closing comment I have for this. What I take from this.
Melissa, thank you so much for taking the time to present for us today. And I'd also like to thank everyone who tuned in today. If you're interested in information on how you can travel with NatHab, please give us a call at the number on your screen, or you can send us an email at info@nathab.com. Our adventure specialists are happy to help you out. Join us tomorrow for our next Daily Dose of Nature. You can check out this week's lineup, including registration links, on our website at nathab.com/webinars. We did record today's presentation, and we will have the replay available on our website soon. With that, I will conclude the webinar. Goodbye, everybody. We will see you next time.